show you, which is going to be a running joke for the entire semester, I think. With the eggs. Allergy advice contains eggs. So, on the egg carton. So, yeah. What?
In case it wasn't clear that you were buying eggs.
That needed further clarification. Okay. All right, done with eggs. All right, let's do a quick recap. Is nutrition labeling required for all foods, including eggs?
Like meat.
Gazelle. Huh?
Fresh produce and meat.
Fresh produce, meat, and also small packages within a big package. All right. What agencies regulate nutrition labeling?
FDA and
Okay, Michelle. Yeah, I know.
FDA and FSIS.
Yes, FDA and FSIS of the USDA. FSIS specifically regulates meat and poultry, whereas FDA regulates everything else. Okay, what type of analytical methods are required to obtain the values listed on the nutrition label? This is a typical question I might ask in an exam or a quiz. When I say what type of analytical method, what do I really, I'm not asking for the name of the method. I'm not asking you to tell me what we're analyzing. I'm asking for a category of methods. We talked about them maybe last Friday or Wednesday, I can't remember. Do you have any clue of what I'm asking right now? Okay, they are analytical methods, but no, I'm looking for a bigger categorization that was reviewed. Yes,
They actually like the set official.
Yes,
methods.
official methods of analysis. So this is what I'm looking for, official, primary, reference, okay? So these are the methods that are required when we're using, when we want to determine components on the nutrition label. So you cannot use the secondary method or the quality control method. Okay, so the rest of these is for the remaining of the lecture, so keep those in mind for when you're studying. Okay, so this is what the current nutrition label looks like. So your common components, but here I'm circling trans fat. This was an amendment made in 2003. Before 2003, we didn't have trans fat. Why was it added? What's the significance of trans fat? What?
They realized about some health issue with trans fat.
Yes, health issues with trans fat, especially coronary heart disease. Were you going to say something else, Dane? Yes, okay, good. All right, so it was added for that reason. And trans fat, does anybody know when do we get trans fat in food? Sophie?
Partial or like incomplete hydrogenation.
Yes, incomplete hydrogenation, and then also animal sources of fat might contain trans fat. So the proposed one was proposed in 2014, and it was approved in 2016, and it was supposed to go in effect in 2018, but it didn't. It was pushed to a further date. I think it's 2020, but some say it might have pushed to 2021. But this is what it looks like, and this is a nutrition label that you will be producing in the lab, or Monday Group already produced in the lab. So what striking differences do you see? Let's go with, no, not April Page.
You'll see that the calorie size is a lot bigger, so like it's look like those are
In
deem
your
it as
face, yeah.
they deem it as important now.
Yeah, yeah, the calorie is bigger and bold. Calories from fat is no longer there. What else do you see? Brigitte?
There's like sugar in food.
Added sugar, that's true. Katie,
I was gonna say added sugar.
you were gonna say added sugar. What else? There is something. Okay, Laura.
They changed the 4 vitamin minerals that are at the bottom.
Yes.
To view them to reflect public health concerns.
Yes, so they no longer, initially vitamin A and vitamin C were of a concern. Now there's fortification and supplementation. So every orange juice you have almost vitamin C added to it. And milk, obviously, you have vitamin A, and then flour is enriched with vitamin A. So we don't have concerns here. But vitamin D is exposure to sun, and there is lower exposure to outdoors. So you have people with more deficiency or prone to deficiency in vitamin D. So it's there. And the one other one that was added, so calcium and iron remain the main ones here. Calcium and iron both remain. And then the addition is potassium. Why do you think they added potassium? Okay, Laura?
Because of its role in blood pressure.
Yes. So it has role in blood pressure and also prevention of heart disease, and also for good bone health as well. Muscle and bone health. Okay, so one day this will be in effect. Okay, so these are the main constituents that you would see in the label. And then these are the daily reference values. That means the value that is recommended for intake per day. So you need to know all of this by heart. And these. No, you don't. These are FYI. So this is, so you don't need to know these. Yeah, but anyway, these are the vitamins and minerals, and we call it reference daily intake, RDI, for vitamins and minerals. Now, what you want to know is the rounding rules. So when something is less than 5 calories, you basically can express it as 0 calories. So if a product gives you per serving 1 or 2 calories, you just say calorie free. And then for total fat, so if you have less than 0.5 grams, that is expressed as 0. So these are handy when you're actually formulating your, let's say, capstone, and you want to report your nutrition label. So you want to know how to round and in what increments you would report them. So how do we determine caloric content? It's mostly done by calculation. I mean, you can't physically measure the calorie in the calorie bomb. You put the food and combust and measure the energy. Yes, of course, I knew this is going to happen. So, yeah, the people before me leave that on, so it's warming. It's cooling down right now. We have a few seconds. But anyway, so calories are always mostly by calculation. So what's the calories from protein per gram? 4. Carbohydrate? 4. What else we have? Fat? 9. Great. Alcohol? 7. So yes. Okay. And then when we determine the calories, so we add all of the grams and calculate the calories. Sometimes if we have high amount of dietary fiber, we take the total carbohydrates, subtract dietary fiber, and then take the remaining grams and then multiply by 4, because dietary fiber do not contribute to caloric intake. And we usually see that it is, now it is 29 seconds to warm up. Okay. Calories, sometimes when you see it with a capital C, that is kilocalories. So 1 gram of carbohydrate or protein is 4 calories or kilocalories. Calories with a capital C. So the next slide is talking about protein quality. And when you want to report the protein quality, or report the percent daily value of protein, it is different than any other component because there is the digestibility factor of the protein, and also there is the amino acid component, the essential amino acid component of the protein. So not every 1 gram of protein is going to give you one absorbable or available or bioavailable 1 gram of protein, because all proteins are digested differently. So we have 2 measures of protein quality. We'll go over them in detail in chapter 24 when we cover protein characterization. But one of them is the protein efficiency ratio, and it is mainly for infant food because it's based on measuring growth upon consumption in baby rats. And the other one, it's also a bioassay. We're involving rats, but here it takes into account bioavailability of the nitrogen by looking at amount of nitrogen intake versus the amount of nitrogen that's excreted with the poop of the rat. And then you can determine protein digestibility that way, but then you take into account the corrected amino acid score, which is the score of the most limiting or the first limiting amino acid or essential amino acid. So if in wheat, for example, lysine is the limiting amino acid. So it is limiting, that means it is the essential amino acid present in the lowest amount. So the score of it is based on the required intake and how much of it is present in 1 serving. So you get a score, that score relative to a complete protein. So relative to a complete protein, you get a score anywhere between 0 to 1. And then the protein digestibility can also be anywhere between 0 to 1 because it's a relative to a reference protein. So relative to casein, for example. Then the score, the PDCAAS score would be out of 1. So 1 would be the highest, most available, and anything less would indicate that it is of a lower protein quality. So 1 gram of casein will have exactly 1 gram that is bioavailable, whereas 1 gram of pea protein is not 1 gram available. Pea protein has about 0.8 PDCAAS. So you take that value and you multiply it by the grams of protein. So if you have 10 grams and if you have a PDCAAS of 0.8, then only 8 grams is available. So 8 out of the 50 grams is what required per day. So 8 out of 50 will give you the percentage of daily value. Okay. So which one of this is correct? Give a wild guess. Karin?
I would say all of the above.
You want to say all of the above? Hold that thought. Everybody agrees? No, some shaking. Muaf, what do you have?
B and C.
B and C. And D. Okay. So all of this. For young children, infants, you want to put the percent of protein because it's important for their growth, percent daily value. And then obviously if you're making health claim related to protein, and if you're making food specifically for athletes for muscle regeneration. So we don't know, we don't put that for reduced calories. Protein is not the main concern for reduced calorie foods. So of course, we have to keep government regulations in mind, so that's why there is compliance with the nutrition labeling. So there are rules that we have to follow. The compliance has to start with collecting of sample. We'll talk about that in chapter 5. So there are a certain number of samples that need to be collected for determining the composition that goes on the nutrition label. Method of analysis, again, we want to look for official methods of analysis. FDA suggests AOAC methods unless other method is specified in the CFR, Code of Federal Regulation. And then the FSIS also suggests USDA Analytical Chemistry Laboratory Guidebook methods or AOA methods if not in the guidebook. So these are rules for compliance. In addition is the level of compliance, which is very important and you need to know this for real. So if you are fortifying or adding nutrients to the food, you're adding vitamins that were not originally present, or you're adding mineral or adding protein for a claim, or dietary fiber or potassium. Anything you add that is not native to the food or the ingredient, you have to make sure that what's on the label represent at least 100% or more. So what you put in the label, and when you actually get audited and they take sample and they measure it, and if it turns out to be 90% of what you claim or 80% of what you claim, you're not in compliance. So it has to be 100% of what you claim or higher. Now, naturally occurring, endogenous, that means present already in your ingredients and formulated food. So all of these specific, these are different categories, the calories, sugar, and total fat. This is different category, but all of these, it's okay to be 80% of what's on the label or higher. Okay? So if it's less than 100%, that is fine. So there is more of a leeway here. But those of concern, calories is of concern, sugars, total fat, saturated fat, cholesterol, sodium, they're all of concern. So these, you cannot have less than or more than 120% of what you claim. Let's say, you have 10 grams or 12 grams, no, 13 grams of fat, and you're claiming only 10 grams of fat, then you are not in compliance. Okay. Nutrient content claim, that means those that are free of salt or free of calories, low, lean, that means low in fat, light, reduced, all of these. Good source of, more, high, there are a certain amount in the food that you can have to claim these different terms. So for example, to claim calorie-free, you need to have less than 5 calories per reference or standard. If you want to say it's reduced in calories, it has to have at least 25% fewer calories than a reference product. So let's say we're talking about a yogurt and a reduced calorie yogurt. So your yogurt, the original one, is your full fat yogurt. So your standard reference food that is not low in calorie cannot be low in calorie. So the reference food would be the whole fat food. And this is for your reference as well. It's not something that you have to remember. But again, it illustrates when you can claim that it's free in fat versus low versus reduced, etc., and comparing it to a reference food. Same for the remainder. So all of this is for your reference. Okay. Last thing is the health claims. So there are many health claims that have been approved by the FDA. So some of them is, for example, calcium and osteoporosis is approved by the FDA. So if your product is high in calcium, you can put that claim on your label. Dietary fat and cancer, sodium and hypertension. So if your product is low in sodium, you are allowed to put this claim. Same with everything else here, and there are many more. Okay, so that's that for nutrition labeling. So we're moving on to chapter 4, data or evaluation of analytical data. We'll be doing that the entire semester, so it's good to have a refresher. I'm sure you've done this in high school and then a little bit in your stats class. So this is just a refresher. So what's the correct answer here? Brigida?
I think A. C is accuracy.
Yes, that is very true. So it is A. Whenever you have lower standard deviation, then it would be more precise. But hold that thought, because I'm going to give you an example later on. When standard deviation is not a good reflection of precision, you need something we call coefficient of variation. And I'll give you that. I'll talk about that later on. This is the opposite, and this has to do with accuracy. Okay, so when we are running a sample, I said that earlier, you never run one sample because you want to make sure that you want to trust your results. In order to trust your results and to think that they're reliable, you have to run the experiment multiple times. So you must run your sample in at least, I would say, triplicate. Some people do it in duplicate and call it a day, but at least in triplicate. Sometimes you need to do 4 or 5 replications. Why? Because if the experiment is tedious and lengthy and a lot of steps, there's a lot of errors. So the more number of replications, the lower is your error. Okay? You reduce the error coefficient when you do multiple replication. Or you reduce the impact of error on your actual decision of the data. So we start off, because you do replication, you start off knowing what your mean and median are. Mostly we're working with mean. We're not going to work with median at all in any of our data sets. So the mean is important. So you have your replications, then you calculate your mean by averaging, adding and averaging your data points. So you have your mean. And from there, you look at your reliability of analysis by looking at accuracy and precision. So how close your mean is to the true value. And what's the standard deviation and coefficient of variation associated with your mean. And looking into the errors. So your standard deviation and coefficient of variation can indicate the extent or how much error there was in your analysis. Specificity, we talked about it last time, how specific your method is. Are we measuring carbohydrate or are we measuring glucose, for instance? Are we measuring nitrogen content or are we measuring protein specifically? Sensitivity and detection limit. So do you know the difference? It's okay if you don't know the difference. Yes, Brigida, you know the difference?
I think the detection limit is the lowest amount that a method or equipment can detect. Sensitivity is how we can detect even the smallest change.
Yes, exactly. Very good. So detection limit, Brigida said, which is correct, is how the lowest amount or concentration that a method or an instrument can detect. So, in other words, threshold. Threshold means the same thing. Detection limit or threshold. Sensitivity is if you have 2 samples, for instance, and they differ in 0.1%, some methods might detect that. Another method might not detect that 0.1% difference. So the smallest change that the method can detect, the more sensitive the method is. And then oftentimes we deal with curve fitting. So mostly in food analysis, we're going to have linear relationship with doing linear regression, and most of the time you have an independent concentration factor, and then you have the dependent factor, which could be absorbance, for example. The absorbance you measure, and then you relate it to concentration. So we will be plotting a lot of linear regression and equations of the line that we will use to predict the concentration in our sample. So correlation coefficient is how well the data fit a straight line. And then reporting your results, and we will be dealing a lot with that. I'm talking about it next week in lab, is significant figures. So significant figures, you have to know how many numbers you will have to report and how many decimals after the decimal point you would need to report. So obviously you won't report 10 decimal points. So you want to know, do I need 2 decimal points? Do I need to report 1 decimal point? And how do we determine that? We determine that based on the balance we use, or the accuracy of the pipette we're using. So we're going to talk about that. So once we learn how to report our significant figures, we will hold you accountable for it for future labs. So when you calculate percent fat, how many significant figures do you need to have? So you will learn that and report your data accordingly. And also you will learn how to reject data points. So for example, in the caffeine lab, we will have 4 replications. And each group will be doing 2 reps. So there is a chance where 1 rep might be off, completely off. So it will mess up your accuracy and mess up your precision. So there is a way to determine whether or not you can throw out that data point and go back to a better accuracy and better precision. Okay, so now time for extra credit. So pull out a piece of paper, put your name on it, and let's solve some problems.
Last year I had it shorter, just in general.
Okay, ready? All right. So let's start from the very beginning. Here is a data set. So we determined moisture content of a sample, and we had 5 replications. And these were the data collected. What would be your mean? What would be your median? So do the calculation, and then someone will volunteer to state the value. All right, whoever has the mean ready, say your name first. Sammy. 82.56, that is correct. What about the median? Say your name first.
So we have 82.
82.63. Your median is the midpoint. And if you have even numbers, even replication, you take the two in the middle, you average them, and that would be your median. So this is it, and pretty simple. So let's look at that again. You've seen this in high school, most likely. So which of these have good precision? Go ahead, Dan.
A and B.
A and B have good precision. That means your data points are close to each other. So here and here. Bad precision, obviously, the other two, right? So data is scattered all over. Which ones have good accuracy? Okay, Paul? Huh? B has good accuracy. Is there anything else that might have good accuracy here? Say your name first. Alice? Yeah? What's that? D. Although precision is bad, but look at it, it's kind of around the center here, so if you take the average, it will potentially be close to the true value. Okay, so bad accuracy, obviously these two, okay? So this one has bad precision and bad accuracy. All right, so in terms of accuracy then, so when we want to determine the accuracy, either we have a reference number somewhere where we have a report published somewhere that we go to. So for example, when you do the proximate analysis lab, a lot of the foods that we have values on the USDA website, their actual reference value. So you would go, okay, what was my fat content? Then this is how much I got fat, and the real value would be the one published by the USDA because it has been validated. Okay? So in this case, your absolute error is the difference between your average and the true value, and it will be an absolute. So you don't have to report it as a negative value if it is negative. It's an absolute error. And then a relative error, that is the difference divided by your true value. Okay? And then percent relative error, which is always what you report as a percentage, you just multiply by 100. So you get percent relative error. So anything less than 10% is good, less than 5% is excellent. So when you have excellent accuracy, it would be less than 5%. But if it is less than 10, it's still acceptable. All right, so let's do this. You are using a mechanical pipette, and usually mechanical pipettes we calibrate. So if you determine your accuracy and it is off, that means you need to calibrate your pipette. Okay, let's get those values. What is your true value in this case? 1. Yeah, the mechanical pipette is telling you that it is calibrated for 1 ml. So it's 1. You know what you're doing, right? We're getting the average by just adding and dividing by 3. The true is 1. And the absolute error is the difference between the mean and the true value. Relative is the difference by the mean, by the true value, and this is multiplied by 100. Is anybody ready? Okay, Gazelle, go for it.
So the mean is 0.9961.
Yep.
True value, should I say all of them?
Yes.
True value is 1. The next one is 0.0039.
Yes.
And the next one is 0.0039.
Yeah.
0.39%.
Okay, yes. So that is correct. I have it here in the negative. It's okay. It just gives me a direction. It gives me direction that my mean is lower than the true mean, but you don't really have to have that direction. Yeah. So there it is. Okay. So in terms of precision, you want to know how to calculate standard deviation, because on a test with calculations, I won't be providing you with the equation. So it is really simple. It's the square root of the summation of the difference between the mean and each data point squared, and then divided by n minus 1. N is your number of replications. So if n is 3, then it's divided by 2. If n is 4, then it's 3. So that's your standard deviation. Now, coefficient of variation is very important, and I'll give you an example for why it's important. So the coefficient of variation is basically you take your standard deviation, so you cannot calculate your CV unless you have your standard deviation. So you take your standard deviation and correct it by the size of the mean. That means you divide it by your mean, and then you multiply by 100. It's a percentage. So I have here an example to illustrate why it is important. So let's say we have two methods. We have near infrared, which is a quality control online kind of method to determine a composition. So near infrared spectroscopy, and then you have DOMAS, which is a nitrogen analyzer-based method. You analyze nitrogen. What is this? I don't know what I was thinking. My daughter is taking the driving test right now, so I'm nervous. Okay, so DOMAS, it's measuring nitrogen content and converting to protein, and this is a method that is calibrated for measuring protein content. And I have wheat flour, and I have an isolate of a protein isolate, soy protein isolate. I measured my wheat flour. It turned out to have 12 plus or minus 1.2 standard deviation. I measured my SPI using DOMAS, and it gave me 92% plus or minus 2.76. 67, 76, doesn't matter. Okay. Which method is more precise? Yeah? DOMAS is more precise. Why then?
Because the coefficient of variation is lower.
Exactly. Very good. Thank you. So here, if we take the standard deviation and divide it by the mean and multiply by 100, I get 3% coefficient of variation. So when I correct by the size of the mean, I get 3%. Here, I get CV of 10%. 1.2 divided by 12 times 100. So here, although the standard deviation is smaller, you would think this is more precise, but the size of the mean is different, very different. So I have to account for the size of the mean. That's why when you guys write up your lab reports and have data every week, I ask you for coefficient of variation. I don't ask you only for standard deviation. So you have to calculate standard deviation and get the coefficient of variation so you can correctly speak to the precision of your method. Because we will be comparing methods. Okay, so, alrighty. Another thing that we usually calculate is something we call confidence limit or confidence interval. So this is the interval within which you have some confidence where your mean lies. So usually we go for 95% confidence. So this would be the range when you're 95% confident that your mean is within that range. Okay, so we need to use tables. So for replications greater than 25, we use z-value tables. For replication less than 25, we use the t-value tables. So this is your this is what you need to calculate. You need to calculate this value, and then you will have your average plus or minus this value. That would be your range. That you have 95% confidence or 90% confidence, depending on the t-value that you choose. So this value here, standard deviation divided by the square root of n, or number of replications. This value here is what it has also another name. We call it standard error. Okay, so the standard deviation divided by the square root of your replication is standard error. Okay, so let's do this, and I need to give you the t-value. So the t-value for the confidence interval, I'm looking for the t-table. That should be somewhere in my t-table. So if I'm going to go with 95% confidence and I have 3 replication, so my degrees of freedom is 2, so the number that I want is 4.3. So my t-value is 4.3. That is the 95% confidence and 2 degrees of freedom. 4.3. Whoever is ready, anybody? Nobody's ready yet? Anybody? You done, Brigida? Yes? You ready to tell us?
Mean is 0.9961.
Yeah.
As I tell you, I got 1.931.
What did you get?
1.931.
0.00 what?
Oh, it's 1.931 times 10 to the negative 3.
Yes, okay. And then CV?
I got 0.194.
Yeah.
And the last one is 0.991 to 1.001.
Oh, so you calculated the actual numbers. So what I usually report the confidence interval two ways. You can report it plus or minus the actual value you get, or you can report it plus this and minus this, like the way you did. The way you did is correct too. So there are two ways of doing that. Okay, so hold on to that piece of paper because we're going to continue with it on Wednesday with the rest of the lecture, and then I'll collect it. When I ask you to write up something and then turn it in for extra credit, take a picture of it so that you have it too. You have those calculations, okay?
The next class,